Hello again, higher algebra students. Back here with the first lesson of the second unit. This is exponent laws. Deal with a lot of exponents in this unit. Jumping into it, goal of the day, I'll be able to explain the laws of exponents to my classmates and be able to simplify problems involving exponents. Question on the bottom, famous miracle on ice game occurred in Lake Placid, New York. If you went right to that when we got onto this slide. So looking at simplifying problems involving exponents and looking at these exponent laws. Just a reminder, an exponent here is that n in this problem. So this would be would read as x raised to the nth power, or x to the n. X is considered the base and n is the exponent. So just what do these mean? Expanded form here would be like 5 to the 7th would be 5 times 5 times 5 times 5 times 5 times 5 times 5. Okay, so it'd just be 5 multiplied by itself. Of course, the common mistake here is to do 5 times 7, but it's not 5 times 7, it's 5 times 5, 7 times. And so keep that in mind. So this would be 11 times 11 times 11. And this would be 44 times 44 n times. Okay, so this would be whatever n would be. It could be 10, it could be 100, it could be 1,000. It would obviously be a very big number if n was something bigger than 5, 6, 7, 8. And so, but it's just multiplying 44 times itself, however many times we set it to be. Simplified form, on the other hand, would be taking the expanded form here, which like we see here, and just saying, well, this is 3 to the 6th power. Okay, it's 3 times itself 6 times, or 12 times itself 4 times. Okay, and that's just, again, a shorter way of writing it naturally, since they mean the same thing, and this would be more efficient. So mathematicians do 3 things in general, and this is dating back to well before we were alive. Noticing patterns and relationships, so looking for patterns in the numbers, in the trends. They describe those patterns and relationships, and they generalize them. And so that's what these exponent laws do. Is the exponent laws, the specific problems they apply to could look any different number of ways. It could have variables, it could not have variables, it could have a big numbers, small numbers, whatever it happens to be. But what it is the idea that they're just getting the pattern and generalizing it. And you'll see it in the first 3 of the 5 laws I show you here. So these 3, take note of these 3. Product of a power, what that just means is if we have the same base, like we do right there, and they go to their own exponent, all that equals is just the sum of the exponents. So for instance, a to the 3rd times a to the 4th would just be a to the 3 plus 4, or 7. Okay. Now the second one here is power of a power. So you can see this would be like a to the 3rd, but to the 4th. Now keep in mind that's like a to the 3rd times a to the 3rd times a to the 3rd times a to the 3rd. So this is a little different. This is actually a to the 3 times 4, or a to the 12th. So power of a power is different than just multiplying with the product of a power. And then finally, division of powers. Here, this is, now we've got the a to the m over a to the n on the 3rd one. And so that just ends up being, so if we have a to the 4th over a to the 3rd, that would just be a to the 4 minus 3. And again, a could be 2, it could be 10, it could be 50, whatever it happens to be. But those are the big 3 right now. So you add the exponents, multiply the exponents, or subtract the exponents, depending on the type of problem. Again, this would be something to have very near you in your notes moving forward. So, product of powers. So 2 to the 3rd times 2 to the 6th would then be 2 to the 3 plus 6, or 2 to the 9th. Okay. Here you can see it's done for you in the next 2. So we've got 5 to the 1, 1, 1, and 1. So that's 7 plus 1 plus 1 plus 1 plus 1, or 7 plus 4, gives you 5 to the 11th. Here, 4,000 to the squared times 4,000 to the 33rd is just the sum of those 2, or 4,000 to the 35th. Again, needs to have the same base. Notice how this is, here we've got a base of 2, here's all these base 5s, here's the base 4,000s. So it needs to have the same base, but that's how you would set that up. So in the end, there's just a product of powers kind of final note there. This, of course, is 4 plus 2. Okay, power to a power. So you can see here, this is written a couple different ways. 4 to the 5th to the 7th, or 4 times 4 times 4 times 4 times 4, which is 4 to the 5th to the 7th. Okay, so these are the same thing right there. But in the end, what the power to a power rule told us is so 4 to the 5th to the 7th is just 4 to the 5 times 7. Okay, again, if when it was just 2, if it was 4 to the 5th times 4 to the 7th, that's different. Okay, that's the product of powers. So that's the 5 plus 7, but this one has the double exponent there. So it's 4 to the 5th to the 7th, which is different. And so that's 4 to the 35th here. Sorry, I almost said 12th. And again, just to keep in mind, this one here, up here, would be 4 written 5 times, and then 4 written 7 times, and just multiply those two. This is 4 written 5 times, and 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 4 written 5 times, all the way until we've written the 7 sets of 5 4s. And so fundamentally different problems there in terms of what we have. So this was 4 to the 12th, this is 4 to the 35th. Here, 12 squared to the 9th, again, would be 12 times 12, 12 times 12, 12 times 12, 9 times, which is 12 to the 18th, which is just 2 times 9. Okay, because that's power to a power. Okay, down here you can just see one done. 100 times 2 is 200. So keep those separate there. Again, if it lists the base twice, then we're probably going to be adding them there. Here, it did list the base 5 times, but again, we do that 7 times overall, so this was the power to a power there. Okay, here's just one final one. 3 times 4 equals 12. Here, division of powers. So now we've got the 10 minus the 8, which is 2. So I just started with the example here on this one. So that's why it's squared. So when you look at this, this one here, 6 to the 5th divided by 6 to the 3rd, would just be 6 to the 5 minus 3, which is 6 squared. This one here is 3 to the 12th over 3 to the 3rd. Okay, that's what 3 times 3 times 3 is. So this would be 3 to the 12 minus 3, or 3 to the 9. And then finally down here, you can see when that's already done. That's 15,000 to the 1st in the denominator there. So that's just 14 minus 1, or 13 for that exponent there. Okay. So what will problems look like? They'll look pretty complex at first because there's a lot of things being combined, but you just need to break it down. So for instance here, we have an x to the 5th over an x to the 1st. Okay, so x to the 5th and an x to the 1st would just be x to the 5th minus x to the 1st. So in that situation, that means we just have x to the 4th left. Okay, we'll see if we need the fraction bar eventually. Now, similarly with the y's, we've got y to the 6th over y squared, which would just be y to the 6th minus 2, or y to the 4th. And that's it. This is technically just over 1 now, so you can just write it as x to the 4th, y to the 4th. Okay. Now, in this next one here, first of all, we've got 3 times 4. Okay, so you still multiply the numbers. So we do have a 12. And then we've got x squared times... Sorry, stopped to cough there, and I don't know if I'm picking up where I left off, but we've got x squared times x to the 5th. So this is not power of a power. This is product of the powers. Okay, so again, you just add those exponents. So that would be x to the 7th. So this is 12x to the 7th. So you're just kind of doing this part by part and just applying the rules where needed. One like this here, you've got 15 over 3. Well, 15 over 3 is 5. Okay. Uh-oh, now we've got a little bit of a power to a power situation. So we've got m squared to the third, which is m squared to the third, which would be m to the 2 times 3. Okay. So that's m to the sixth. And then we've got n to the first to the third. So that would just be n to the third. Okay. So again, what we've done there is power of a power with each of these. Okay. Now, in the denominator, we've got m times m. Well, that's m squared. Again, we already did the 15 divided by 3 is 5, so we don't have that 3 in the denominator anymore. And then we've got an n. Well, now we've got division taking place here with the powers, and so we've got m to the sixth over m squared. Well, that would be m to the 6 minus 2, so that's m to the fourth. And then we've got n cubed over n to the first, so that would be n to the 3 minus 1, or n squared. Again, there is no more fraction anymore because all that's left there is 1. So I'm just going to leave it like this, and there you go. Okay, now in the second one here, again, we've got negative 5 times 2, so we've got a negative 10. That's set. Actually, let's just leave this for now and finish writing these with that power to a power. So let's leave that as negative 5. Now we've got x to the fourth squared. Okay, so x to the fourth squared, that's power of a power, and again, that's multiplication, so that would be x to the eighth. Okay, and then we've got y to the first squared, which is power to a power, so that would be y squared. Okay, and then here on the second part, we still just have the x squared and y to the third. So now we're just going to combine the ones that are alike here. So we've got negative 5 times 2 is negative 10. All right. We've got x to the eighth and x squared. So they each have their own base, so it's not power to a power. So that's x to the eighth times x squared. And so you just add the exponents. So that's x to the 10th. Sorry, that's a 0. And then finally the y's. We've got a y squared and a y to the third. Again, they each have their own base. So that would just be 2 plus 3. So that's y to the fifth. So we've got negative 10, x to the 10th, and y to the fifth. Notice how I just had to do this by parts. So the first thing I took care of was the power of a power in both of these. And then I went and did the rest of this with the rules that we know, along with just multiplying or dividing actual numbers, in this case 15 over 3 up here, and negative 5 times 2 here. All right. Let's just take a look at a couple of others here. Zero power and negative power. Zero power just means anything raised to the 0. And what that does is anything raised to the 0 is just 1. So for instance, if I have, say, 25 raised to the 0, okay, 25 to the 0 is just 1. Okay, so that's the idea of a zero power. And then a negative power is the idea of having something raised to, say, the negative 1. Well, that is the equivalent of being 1 over a. Okay, or if it was a to the negative 5, that'd be 1 over a to the fifth. Okay, so what a negative power does is it basically puts it on the opposite side of a fraction bar. So as this gets more difficult, what there might be is something like a to the negative 3 over a to the negative 2. Well, being on the opposite side of the fraction bar, that just actually brings that up to a squared and brings this down to a to the third. So that's what a negative power will do, is it will bring, if it's in the denominator to start, like this was, it will bring it up to the numerator. If it was in the numerator to start, it will bring it down to the denominator. So that negative exponent, and if you put a value in there, you would see that. So if we did, say, 5 to the negative 3 divided by 5 to the negative 2, that would be the equivalent of if you just did 5 squared divided by 5 to the third. Okay, you get the exact same answer. So again, 5 to the negative 3 over 5 to the negative 2, and you can check this with a calculator, is the same as just 5 squared over 5 to the third, okay, in that situation. Now, you won't always have two negative exponents, but that's just how it would work in that situation where you, where they're just on both halves, numerator and denominator, excuse me, both sides of the fraction bar. So in general, this zero power, again, as you look at this, 3 to the fourth is 81, 3 cubed is 27, 3 squared is 9, 3 to the first is 3, 3 to the 0 would be 1, and we could keep going. 3 to the negative 1 would be 1 over 3, 3 to the negative 2 would be 1 over 3 squared, or 1 over 9, and you can see what happens, okay? So this is kind of the middle point of this whole chart, and then you can see that 3 to the first is 3, but 3 to the negative first is 1 over 3. 3 squared is 9. 3 to the negative 2 is 1 over 9. And so you can see it would be 1 over 27 would be 3 to the negative third. 3 to the negative fourth would be 1 over 81, and so on. So that's how those all work together there. So here, 55 to the 0, 1. 3 to the 0, 1. 0 to the 0, that one is a little different because we've got a domain issue there. So 0 to the 0, if you put that into your calculator, for instance, that's going to be an issue, and we won't jump into that right now. Mr. Roach to the 0 is 1. Okay, another math teacher, anything to the 0 is 1. All right, except for the one exception, 0 to the 0, which we won't jump into here. Anything to the 0 equals 1. Okay, that's the 0 exponent. Now, like I just did on the last one there, 3 to the negative 1 will be the 1/3, 3 to the negative 2 will be 1/9, and so on. So a negative exponent just tells us to move it to the other side, or negative power. So a to the negative n would be 1 over n, excuse me, 1 over a to the n, and 1 over a to the negative n would actually just be a to the n. So you can see how those just, that negative exponent, how they work in kind of opposite directions there. So 6 to the negative 2 would be 1 over 6 squared, or 1 over 36. X to the negative 7 would be 1 over x to the 7th. Okay, 1 over p to the negative 4, again, that would be this one. So that would just be p to the 4th. Okay, you could say over 1, but you don't have to. 1 over 5 to the negative 3rd would just be 5 to the 3rd. Again, the idea there is that the negative exponent just brings it to the other side of the fraction bar. Okay, so keep that in mind whenever you get that negative, is there's going to be either an undoing of a fraction or inclusion now of a fraction, adding in the fraction, bringing in the fraction. So you look at this one, like we talked about, 9 to the negative 5th goes up top, 9 to the negative 2 goes to the denominator. Okay, so those just flip-flopped because they were both negative exponents, and so it caused it to go to the opposite level of the fraction bar, numerator to denominator, denominator to numerator, and then you could solve from there, which we won't do. Simplifying these, so 3 to the negative 4th would be 1 over 3 to the 4th. So just some examples here, and then you'd get 3 to the 4th, which is 3 times 3 times 3 times 3, which is 1 over 81. Okay. Negative 4 to the negative 3rd would be 1 over negative 4 to the 3rd. Okay, and now negative 4 to the 3rd, again, if it's a, so it's 1 over negative 64, or you could write it as just negative 1/64. Okay, so the idea of it being an odd exponent will keep a negative negative. So that's just a heads up there. If this were squared, squaring always brings it back to positive, because negative 4 times negative 4 is a positive 16, but positive 16 times another negative 4, so what I mean by that is this, negative 4 times negative 4 is 16, negative 4 times negative 4 is 16, but then if you multiply that by another negative 4, that's now a negative 64, so that's that, which would be a little different here. 7 to the negative 1 is just 1 over 7. could say 1 over 7 to the 1, but it's really 1 over 7. Negative 3 to the negative 1 would be 1 over negative 3, which is the same as negative 1/3. Okay. So you get the negative 3 to the negative 1. Again, keeps that negative. Now you do have to be careful here on this next one. If you were to type this into your calculator as just negative 7 to the 0, that would actually be a negative 1 because it reads it as negative 7 to the 0. But when you write it as it's written here, that negative 7's in parentheses, so it's negative 7 to the 0 is just 1, but this is 7 to the 0, and it's a negative, so that's negative 1. Okay, so you'd have to be careful here whether that negative is written with a parenthesis or not. Makes a big difference. Versus this one now, negative 5 to the 0 written without a parenthesis is actually 5 to the 0, which is 1, but it's a negative of that, so that's negative 1. So this one here is actually 1, and this one here is actually negative 1. And we'll talk more and more about that, about the difference between these two. But again, this negative here is with the value. This negative here is for the whole solution here with the raise it to the 0. So two different types of problems there that you have to be careful about. Now here you can see exactly how complicated it could get. But again, anytime there's that negative exponent, we just move it up top. And so what we end up here is just getting another a to the 1 and a squared up, or excuse me, and b squared up there. And then we have like a to the 3rd and a to the 1st would be same base. And so we just 3 plus 1 is 4. And you can see those steps there as you continue on in that one. So not that complicated. It's just about understanding the rules and that the negative exponents move it. So you can see here, this is negative exponent and product of powers in that situation. Now, just a couple more simplifying options here. You do, on this first one, just have to be aware that the way it's written, the answer would be different if it was this, okay? Right now, the negative 5th exponent, negative 5 exponent, only goes with the m. So this would really be 11 over m to the 5th, okay? And so that's makes it just a different answer than if we were to write it as 1 over 11m to the 5th, of course, which is incorrect here because there weren't the parentheses, okay? And so keep that in mind, that you do, again, need to be aware of those parentheses. Here, this is a T. It looks like a cross in that situation. But again, what we've got is a 7 and a T, and then an x to the negative 4, which would mean it's in the denominator. Okay, and again, you could put values in for that. You could put a 1 in for x and a 2 in for t, and that would be 7 times 2 over 1 to the 4th. And you could solve it each way. So if you put a 1 in for x, it'd be 7 times 1 to the negative 4th times 2. And if you were to type that, say, into your calculator, you get the 7 times 1 to the negative 4 would be just 7, because that's 1 over 1 to the 4th, which is 1 over 1, and multiplied by 2 is 14. And similarly, this would be 14 over 1 to the 4th is just 1. And it's not just because it's 1 that it works here. It would continue to be that case. And so, so this is 7t over x to the 4th. Sorry, that's a 4. Next one here, 2 squared is 4. And again, this is over a to the negative 3rd. Well, that just means the a to the negative 3rd goes up top. So this is just 4a to the 3rd. And again, make sure when you move it up top that you change that to a positive exponent. That's what changes when we make the move there. Here, again, n to the negative 3, we'll move that to the denominator, and b squared is already there. Now, these are supposed to be in the denominator, so what do? We just put a 1 over it. Okay, if they're in the denominator, but we don't have anything left up top, then it's just a 1 in the numerator. So that would be 1 over b squared n to the 3rd. And again, you could put values in for that if you wanted to double check that that was your answer. This is more practice. I'll just really quickly, this is 1/3. Here, just make sure to move the x and the y to the denominator, so it's only the 2 up top, and then you have an x to the third, and a y squared, and a z to the fourth that's already down there still. Here, these two just flip-flop, so that's t to the fifth and s to the third, because they are both negative exponents. Here, you still have the 20b in the denominator, but now you also have an a to the fourth that came from up here. And then up here, you still have a 14, and then you get that c to the first that came from the denominator. So just be aware there. Here you've got a couple of negative exponents, so those will swap spots. So you get 4f and h to the third up top, and then you have a 5 and a g to the fifth in the denominator. Everything else stays. Here you keep the a to the fourth up top, you keep the c squared up top. E to the 0 is just 1. You could just leave that blank, or you can put it there. Now we have a b to the negative 1, which has to move up to be b to the first. And we have a d to the negative third, which has to move up, so that's d to the third. And we don't have anything left in the denominator, so that'd be over 1. But again, you do not need to write the over 1. Lastly here, -3 times a -3 divided by a -6 is 3 over 6, or 1/2. So you technically have 1 over 2. Again, that g to the -2 right there, it's just tough to see now, ends up being a g squared in the denominator. The h stays. K to the -2 ends up going down here to be k squared. H to the 0 down here is just 1. Okay, so that's just 1. And now we kind of clean this up from here. So we'd have 1h, or just h, left up top. And then we have a 2, we have a g squared, and we have a k squared here. And again, that's just from moving all of these around here, so that we could, let's see, can I get a bigger eraser here? There we go. So we just took all the negatives and switched them. We did the division of the two numbers there, the -3 over -6. It was a positive 1/2. And then again, the ones, they're just along for the ride. You don't have to write the ones because they don't change our answer there in any way. If you left them, it's fine. They'd just be there along for the ride. And finally, we've covered 5 exponent rules here. The first 3 were the product, quotient, and power to a power rule there, and then we did the 0 and the negative exponent. So a lot to unwrap there, but that's again gives us a lot to work with when it comes to exponents, and we'll start to look at some applications of these as well in the real world. Thank you. As always, if you have any questions, please make sure to ask.